Okay, please. Next speaker is Jnana Rao from the IT Bombay, and it's talking about URANS of Mach 2 Isothermal jet in OpenFOAM. Please say. Good morning.
Good morning. My name is Jnana Rao. I am from IT Bombay, India, and I am presenting URANS of a Mach 2 isothermal jet in OpenFOAM. So I'll just get to the presentation. So this is related to my PhD work, although this was part of the preliminary work that I started on it. So I'll just begin with how I got familiarized with the topic. My primary area of research is jet noise for a supersonic jet. So when I first heard about my topic, what I thought about was something like the image on the left. So that is NASA's X-59. That is supposed to be a supersonic flight, which does not create a sonic boom. So for reference to people who are not aware what that means, it's like setting off a gun that sounds like a knock on the door. Like it doesn't even create a blast sound. But when I had to start my work, I realized I'm not doing anything like the picture on the left. I'm doing something very basic. What I'm doing is I'm trying to simulate a simple Mach 2 isothermal jet, and I'm trying to capture the noise that it generates. So my plan of action initially was I will conduct a RAN simulation. From the RAN simulation, whatever I understand, I'll do a LES calculation. LES is large eddy simulation. And from the LES data, I will sample some data points. And then from there, using the pressure and velocity, I will calculate the noise that the jet generates. However, in terms of understanding what happened was exactly the opposite. I didn't get good RANS results. I went and I basically went forward with the LES anyway. I got poor LES results. I got poor noise results. However, from the noise results that I got, I understood what was probably happening incorrectly in the LES calculation, and from there, what was happening incorrect in the RANS calculation. So at this point, I have to correct something, which is that we are not working with RANS, we are working with URANS. Why is that distinction important? You'll come to know even later on, but primarily, when we are trying to simulate a jet, you have a region in the center, which is the actual jet, which is a supersonic region. And when you look at the governing equations, you will find out that such high speed, high velocity flows will generally have a hyperbolic character. However, the ambient air will have a parabolic character. And it turns out that if you have such a domain where you have hyperbolic and parabolic parts to the domain, you cannot have a steady state solution. So you can't proceed with the RANS. And that was also my experience, although I didn't know about this thing. So I just kept trying with RANS and never getting a solution. But it's good that I know this now. So I'll just briefly mention what I'm trying to compare my results to. So this is an experimental work which was published in 2021. The thankful thing about this work was that they also included, so generally for Mach 2 jet, what we had for reference was a jet called Siner's jet. And that was basically only centerline data for velocity, pressure, temperature. Thankfully, as we are working with turbulence, this recent data set also had some centerline values for the Reynolds stresses. So when I started working in OpenFOAM, I went through what models were available, what solvers were available. And what I came to know is, so there are basically two solvers that people use. At this point in some version of OpenFOAM, the first solver is obsolete, but still I'll proceed. So that is Sonic Foam. From here on, I'll refer to it as SF. The second one was Row Central Foam, RCF. In the course of my work, I also tried a third solver because I couldn't get good results with either of these two. That is called Row Energy Foam. It is an independent solver. It is not part of any original OpenFOAM distribution, but it's independently developed by two researchers in University of Roma Sapienza. The basic difference between these solvers is how the flux is calculated in the cells. I'll not get too deep into that, but that is the main distinction between how they work. They solve the exact same governing equations, but they only calculate flux different. The other thing that I was working with, the other parallel were the turbulence models. Again, here, what I had already seen was that two equation models like K epsilon, K omega were known to not give good results with these jets. So I knew that OpenFOAM also offers some RST, Reynolds stress transport models, which will solve for all of the Reynolds stress components individually. So this is the basic set of what I am tackling within OpenFOAM. And just because we are trying to make results repeatable, I wanted to include this slide because this was what I spent almost 1 year trying to figure out as to what discretization seem to give me reasonable results. I wouldn't go too deep into this, but this presentation I'm sure will be available. So anybody who's trying to reproduce the result will find this helpful. Okay, so I'll get to some of the results. The one thing that I noticed was the jet is supposed to be very highly turbulent. But when I do URANS, I'm getting almost no, none of the small scale structures are captured by any of the two equation models. So these look very plain. These are instantaneous plots. For reference, I'll show you what for one of the RSTM models I'm getting. So I'm not sure if this is visible, but there is far more small scale detail that is visible in the RSTM model as compared to this, which is almost a completely smooth plot. And you can also see the signature in the center line data that I've plotted. Again, you see these jagged lines which show that there are some small scale details which are captured here, and these are completely smooth in the K epsilon model. So now I'll get from instantaneous plots to mean plots. So in general, K epsilon, K omega, Launder, Sharma, K, all the two equation models that I tried, they showed a typical kind of shortcoming. So they had short potential cores. So what that basically means is this red region that you see that emanates from the jet. So that is the region, or that is the distance that it takes for the ambient flow to completely invade the jet. So until that point, there is still some part of the jet which retains its original potential flow or original velocity which it had at jet exit. So we see that all the epsilon, all the two equation models show a very short potential core. And they also overestimated the turbulence. So the first plot that I've shown here is for the velocity. The red plot is the experimental data. And you can see that the flat line represents basically the potential core. And then there is a drop off in velocity. So although some models come close to the value of the potential core length, which is about 10 diameters, they have a very steep drop off. But when you look at the turbulence data, you clearly see that there is a huge problem. So they are vastly overestimating what the value of the turbulent kinetic energy should be compared to the red jagged plot, which is the experimental data set. So this was one of the shortcomings that was very obvious to me when I was starting the RANS work with two equation models. So now I'll get to the RSTM model. In the RSTM model, again, the results were better. If you compare it to these, they are definitely better. But the location of where the peaks are, some of the peaks are too high. So these problems still persisted. So I tried to figure out what's exactly happening. Okay, so as I mentioned, the LES results, the noise results and LES results kind of indicated what's wrong with the RANS result. And the problem was numerical dissipation. So as a rule of thumb, what I would like you to remember, if nothing else from my presentation, you remember this. For a jet, if the numerical dissipation is low, you get a longer potential. So this was one thing that took me 1 year to understand. The basic reason for this is, so as I've shown here in the figure on the right, you see small scale structures. So what happens is small scale structures indicate there are the eddies that should be there in the flow. However, if the flow doesn't resolve these, the eddies will be much larger. They will create much more entrainment and the jet mixes much faster. So that is why you get a shorter potential core. The other problem that I faced was in some calculations, I was getting a longer potential core. So that was another issue that I was not able to figure out why that is happening. And it took me a while to figure that. So I'll just reiterate. The shorter potential core was an indication that the solver plus Reynolds, whatever, the turbulence model together are creating too much numerical dissipation. But what was the reason for a longer potential core? So for that, it again took me a while. So this is a sort of the gist of what I understood. if you look at a signal and you try to find what you get as a time average, you have a choice of what should be your timing, the sampling window. You will see that if the top one is the original signal, if you take a very short time step, you can get a fairly good representation, a smoother representation of the original data set. However, if you increase your window significantly, you will see that you will almost get zero, the absolute long time means as your values. So what was happening basically was that when my time step was too large, the flow gradients were getting smoothened out. And when flow gradients are getting smoothened out, especially for velocity, they affect the amount of Reynolds stress that will be generated. And the issue that I was facing was the Reynolds stress was being under-predicted and the mixing was being under-predicted. Yeah, so this is what I wanted to show. The best solution that I got was with sonic foam and an SSG model, RSTM model with compressibility terms included. And initially, I got good small scale resolution with it, but I was seeing that it was still too long. The potential core was too long. So why that was because when I did the calculation, all I cared about was that I got a stable calculation with the maximum time step. But it turns out that the other models, like the other solvers besides sonic foam, were actually using a much smaller time step. Sonic foam just happened to be more stable with a much larger time step. It was almost 5 times larger than the others. And what was happening was that then the transient term was actually an average over a much longer time period, and it was actually smoothing out all the gradients. So this is what happened when I changed the time step. I changed nothing else in the calculation with sonic foam. I only changed the time step. And you see that the original orange line versus the experimental data for the velocity, the first plot, it almost matches completely. Even for the second and third plots, there are still some ways to go. And it was probably an issue of more resolution because all these calculations were done on a 3 million mesh. But then the issue was that I was going to do an LES anyway. So eventually, instead of doing URANS on a much finer grid, I simply did an LES on that finer grid. And I can also share. So here, for example, if you can see the red jagged lines for the second and third plots versus the blue scatter plot. So that is a comparison of the LES result versus the experimental data. So primarily the LES is the only one amongst all the calculations that I did which was able to capture the early Z, which is in the region of 0 to 5D to 10D, that region much better. So when I reached LES at this point, I simply quit with the RANs. Like I knew what was wrong in the RANs, which was probably an issue of resolution. But if I could do the LES, I just went ahead with the LES. Yeah, so there are other results here. So primarily the two things were for me to figure out why the potential core was too long or why it was too short. So I did that, but also because I used 3 solvers and 5 models, I had 15 calculations in total. So there are other things that I saw, other patterns, but I thought because this is supposed to be only a 15 to 20-minute presentation, I'll keep those results for the final paper rather than discussing it here. Oh, yeah. Okay.
This correct was still that Mach injected thermal.
Yeah. I mean, the initial total temperature, total pressure that I'm using is based on the isentropic condition that is required so that the jet at exit has the same temperature as the amp. And I mean, there is some correction to that has to be applied based on the boundary layer correction for the nozzle, but that data set was available with the experiment. Like they had mentioned what values of pressure and temperature were used. And I also had the nozzle proof. Okay.
It's RANS is not supposed to resolve any some of the structures, which is
models solutions in your unsteady rounds, should be something else. It could be sort of other forms of unsteadiness, at least in the team rounds is supposed to model all of the relevant mechanisms. I agree completely that AES is necessary to objectives. And that's, I think, the community agrees on that. And then it maybe wasn't worth trying so long to look at unsteady ranks, because if you want to unlock the tech ones, you need to
yes. So Elias is correct. Yeah. So I mean, from whatever I understood about URANS, I'm not even sure if the theory or even it's supposed to have a very. I mean, these like you raised this issue. I'm not even sure if URANS is completely accepted as like smooth, because I mean, in essence, RANS is supposed to be averaged, right? But unsteady for averaging always creates the question of how long is the period on which you are averaging. So I believe I could get a smooth plot, but then when I had to use a time step which was very small, I figured then the actual sample, like even comparing, if I assume the LES is giving me the correct time scale, right? And that time scale is of the order of 10⁻⁻⁷, and I'm seeing quite significant fluctuations there. If I'm only averaging for a time period of 10⁻⁶, should it be a completely smooth curve? That's the question. If the time step is too small, should there not be any fluctuations, or should it really be completely smooth?
But probably the product is not a good modeling for this type of even if it's staying or steady.
Yes. Yeah. So
simply use
no. So I'll just try to yeah. So I know that. In fact, I knew I had to do an LES. I was basically trying to initialize my LES with RANS results. And when I was doing that, I could never understand why my RANS results were so far off. And my entire PhD work is with LES. The only thing is I wanted to sort of go back and see why the RANS results were so far off. And this entire presentation is basically not along the lines of what I'm doing in my PhD work. It's just like it was a curiosity that I tried to fulfill, figuring out why the RANS results always show like very short potential cores or very long potential cores. What could be the reason? So my entire work is actually in large ADC, although it's still using OpenFOAM.
So you're raising
Yeah, true.
Unsteadiness you saw in one of your lyrics, but I believe that you must be some kind of aspect. I think that's
okay. So I agree. I mean, the problem I had was I was always wondering. So if you look at the URANS, the unsteady term is d whatever do you mean by dt? That is supposed to be over the time step, right? That it's being calculated. So if the time step is really small, do you expect it to be completely smooth? If the original sample has a lot of fluctuations, it is supposed to vary with time because it is inherently a temporal term. So are you not going to see any fluctuations? That was the big question in my head. Far field, so I'm basically using wave transmissive for pressure. Yes. And so I was trying to use wave transmissive for pressure, and I had to basically try different boundary conditions for velocity. And the one that worked best in the end was an inlet outlet fence, which is like a no backflow outlet or no backflow inlet. I don't remember exactly, but it was one of the inlet outlet or it was outlet inlet. One of these things that I had to use. So I tried zero gradient. I didn't get good results with that. I tried advective, I didn't get good results. I tried even wave transmissive, setting the field as U. The one that seemed to work was inlet outlet. It seemed to give me no reflections or any of those issues.
Maybe it is used to see it.
Yeah.
It's not used.
This was a question that was asked by ISRO, my funding agency, that are you sure this is non-reflective? So the best I could do at that time, and they gave me like 2 days to answer their question, was I did the calculation for like a time period where I tried to actually plot the pressure. Like I tried to show an animation of the pressure. And it doesn't seem to have any reflections. Like that's the best I could do in a short time. But so far, I have had erroneous cases where there have been reflections. So I sort of have an understanding of what it looks like if that error is present. But in these calculations, I didn't see that. It's not a foolproof way of figuring it out. But I have some confidence that I didn't see the reflections in these calculations. Because when I see those reflections, I can spot them like, or I've had calculations where I had faced problems.
Please share your screen. Okay. Now we see your screen. Okay.
Can you see my presentation?
Yeah, we can
Okay.
see. Okay.
Okay. Hello, everyone.
Yes, please. Let me introduce you, please.
Sure.
Next presentation is from Chandan Bose from the University of Glasgow in collaboration with Edinburgh and Birmingham about effect of sweep on the leading edge vortex dynamics of plunging wings. Please, on stage.
Thank you for the nice introduction. Hello, everyone. I'm really apologize for this mishap with the technical issue, and I'm sorry that I couldn't be present there in person, but I will try to share our collaborative work that is ongoing to understand the physics of the swept wings, particularly to understand the effect of sweep on the leading edge vortex generation on this kind of flapping wings. You might notice that in our title, it was giving us pitching wings, but due to some experimental limitations and for the validation cases, we redirected our work for a different kinematics for plunging wings, and which is more interesting to present. So I decided to actually present this work today. And before I go into the work, I am a newly joined assistant professor at the University of Birmingham. And this work is in collaboration with Dr. Kiran Ramesh from the University of Glasgow, and the work is led by the PhD student Alex Kavana. So what is the motivation for this present work? The motivation comes from nature, and particularly the particular species of the birds who can sweep their angles of the wing, and also can modify the effective angle of attack to enhance their aerodynamic performance. And as humans, we always try to do biomimicry and try to understand the physics of the nature and then apply that to engineering systems. And here you see an example where an unmanned air vehicle has been built with varying sweep angle to mimic the physics which we see in the natural flyers. Now, just to confirm that this study will be carried out in the Reynolds number of the order of 10 to the power 4, and which is in the region of, you can see in the middle region of small birds. And so it mimics the physics that we observe in the nature for a larger insect or small birds. And our study is completely on understanding the unsteady nature of the leading edge vortex. And as you can see that it is quite complex and at this low to moderate Reynolds number regime, and has very rich flow dynamics within it, which is the main focus of this study. Now, what is the main research questions that led to this work? So the first question, the broad question that we try to understand is, what effects does sweep angle have on the LEV formation, growth, separation, and breakdown? And how can the kinematic and the geometric changes improve the LEV stability? Now, given that it's a 10-minute short presentation, I cannot really tell you everything, but I will mostly focus on what effects does the sweep angle have on the LEV initiation. Now, just to clarify the kind of geometry that we are dealing with, we normally have studied many different sweep angles, many different aspect ratio, and many different cross-sectional profile of the wing. But for this short presentation, I will mostly present the aspect ratio 3 wings, and which is NACA 0008 profile with 3 different sweep angles, 0 degree, 30 degree, and 60 degree. Now, this is a representative figure of the experimentally manufactured wing that we are going to test in the water channel in the University of Edinburgh to measure the flow field, the forces, and also to visualize the flow field using PIV. And for this particular presentation, I have chosen a ramp kinematics. As you can see that the plunge, that is the translational motion rate, is a ramp here, which is given in the red curve. That's because the h dot, that is the rate of the plunge divided by the free stream oncoming velocity, gives us the effective angle of attack, and which also gives this resulting plunging kinematics, which is shown in blue here. And as I want to first confirm that we are using this Palette-Alamus based model based improved delayed detached eddy simulations. And as you all know that the main difference from this from the variant of DES here is the turbulent viscosity formula is based on a modified length scale, d bar here, and which is based on the wall distance for the RANS model and the mesh size based length scale based on the LES model. And now, before going into the actual results, I want to show you the validation part where we have compared the load. We had CL is the coefficient of the lift with the flapping cycle for a pitching wing with the experimental results observed by Otomo et al. And we see that we are quite close, although it can be improved, but we accept it as a reasonable comparison with the experimental results. And in the left, you can see the very low fluctuation scales of the turbulence at the Reynolds number of 20,000 that we can capture by this IDDS model. Now, just before going into the physics, I want to show you the comparison between the unsteady RANS and the IDDS results. So this comparison has been done for canonical plunge kinematics, which is sinusoidal in nature. And as you can see that in the coefficient of lift, it is almost very close to each other. Only there is some fluctuations capturing at the peak, which denotes to the fluctuation in the leading edge vortex. And as you can see in the Q2 criterion flow visualizations that in comparison to the RANS model, we can capture way more small turbulent structures, and the interactions between the leading edge vortex and the tip vortex here very clearly using this IDDS model. So this is the motivation for us to choose the IDDS model for our further investigation. And so this is to clarify the coordinate system. So our origin of the coordinate system is at the root of the wing, and the X and Z axis is along the chord and the span. Now, so the first result that I want to show you that how the leading edge vortex is initiated. So as you can see in this, and the red dot gives you the kinematics, that is the h dot by u, the effective angle of attack. And you can see that as the downward ramp motion of the wing progresses, there is some peaks and troughs of the lift curve. And in the downward motion, the lift actually first linearly increases, then it goes down, and you can see the below mentioned Q2 criterion flow visualization techniques that how the leading edge vortex is initiated as the load, aerodynamic load changes. And I am going to discuss this in further details in the upcoming slides. And so here, let us look into slowly how the leading edge vortex is generated and how we can capture this. So this is the case of the sweep angle 0 degree. And of course, you are seeing the flow visualization for the half wing. So basically from the root to the tip, and you can see that in the right figure is the pressure contour, that is the coefficient of the pressure, and which basically shows you this blue circular portion and the blue lines. This shows you basically the formation of the leading edge vortex leg, which is represented by the negative pressure. All right. And as we go with time, we can see that this leading edge vortex gets shade, and the leading edge vortex rings becomes nonlinear in nature. And that's why you see these wiggles in this blue negative pressure regions. And as we go to the non-dimensional time 3, or the convective time 3, we see that the leading edge vortex has been completely nonlinear, and it started interacting with the tip vortices were leaving the trailing edge of the wing. And since the leading edge vortex is passing over the trailing edge, we don't see any negative pressure regions in the pressure contour of the surface. Now, keeping this in mind, if we go to the next sweep angle of 30 degree, we see that the flow dynamics has changed quite significantly with respect to the no sweep angle case because of the geometry. Because when we introduce sweep in the geometry and it undergoes a ramp plunging rate, then it changes the acceleration significantly due to the geometry. And here you can see that at the root region in the middle of the wing, we see that the leading edge vortex strength is quite less, and it is not, the whole leading edge filament is not continuous, and it is divided into two parts of the sweep angle. And as we go further, we see that in this two swept part, the leading edge vortex gets shaded separately. And as like the previous one we saw compared to this convective time of 2.5, here we see that the degree of nonlinearity is quite high. And as we progress, we saw that this coherent leading edge vortex legs get shaded from the trailing edge, and with time they join again and form arch vortex, which is very clear from this figure. And this physics becomes more dramatic as we go towards the very high sweep angle of 60 degree, and we can see that there almost the leading edge vortices are attached due to this high sweep angle, and we do not see any leading edge vortex separation leg in terms of the low pressure region. And as we proceed with time, we see that even the whole time span till it leaves the trailing edge, the vorticity becomes quite attached, and they are not separated. And another noticeable thing is that in the root of the wing, the strength of the leading edge vortex increases, which gets feed from the vorticity from the leading edge of the corner root. So that's another important thing to notice here. Now, we need a way to quantify this effect. All right, so till now I have explained you qualitatively what happens in the initiation of the leading edge vortex, but we have a way of measuring the suction at the leading edge of the wing, which can be done in terms of the leading edge suction parameter, or LESP, which is established in the literature. It is nothing but a measure of the leading edge suction, which is measured by this A0 parameter, which is nothing but the Fourier coefficient of the first order term of the bound vorticity of the wing. Now, till now, this measure has been applied for 2D cases, and we have no knowledge how we can extend it for the 3D flows. But so we tried to explore this measure to apply to our cases. And here notice that as the leading edge vortex grows, initiates, the value of this LESP or A0 increases, And when it crosses a critical value, the leading edge vortex separates at some point. Here you can see in the dark green phase, all right, with time. And now when we calculate this value, the LESP value for our cases, we take in a quasi 3D manner. That means we calculate this separately in different 2D planes along the span. So at the tip, at the root, and at the 40% span. Now for the unswept wing, you see that the trend is all the same for all three planes, as if like as we go with time, the value of this leading edge suction parameter increases, and beyond a critical value it decreases, which denotes the separation of the leading edge vortex. But as you can see that for the 40% span and the root planes, the leading edge suction parameter is quite higher compared to the tip region. And you can see the corresponding stages of the flow fields, which I have already explained. Now, so this is pretty clear that even for unswept case, as we go in different spans, this leading edge suction parameter varies. All right. Now, if we go for the 30-degree sweep angle, we see that there is a significant change in the trend. That means previously the root plane, the leading edge vortex suction parameter was the highest as in the 40% span, but in this case the tip and the root planes are actually at the same, and the 40% span case gives us the maximum value of the leading edge suction parameter. However, the trend is the same, that as we go with the time, after a beyond critical value of the leading edge suction parameter, we see the leading edge vortex gets stated, as I have already explained qualitatively. Now, as we go to the third case of the 60-degree sweep angle, we see again the trend changes. That means the suction measure corresponding to the root plane is the minimum here, and then 40% span plane shows the maximum leading edge separation suction measure, and which is pretty clear, as you can see that in the 40% plane case, the strength of the leading edge vortex is quite strong. Now, summarizing this fact, as if we compare the case at the root of the wing, we see that as we increase the sweep angle, our strength of this LESP parameter decreases. That means that it means nothing, that as we incorporate more and more sweep angle, the strength of the leading edge vortex becomes more and more weaker. Now, we also try to make a link with the circulation, non-dimensional circulation value, this gamma divided by UC, and we see that the trend shows the same and is proportional to the square of the leading edge separation parameter. So what can we conclude from there? We can conclude that the strength of the leading edge suction, which is measured by this LESP parameter, reduces as the sweep angle increases. It suggests that the LEV initiation is more and more weaker. And so to note that it is calculated on a Z normal 2D slices, but we did not incorporate the increase in the Z direction flow. So of course, it can be corrected with more stringent LESP criteria. And the distribution of LESP across the span changes with the sweep angle. As the lift distribution becomes more and more tip loaded for a more highly swept wing, and there are more to study. So this presentation only shows you the initiation of the tip, leading edge vortex, but there are more to study about its interaction with the tip vortex and the breaking down of these nice coherent arch vortices as the degree of the turbulence increases. So that I will keep for a future presentation. And the future effect will actually go back to and address our main research question that we posed, and the results will be validated with the experiments carried out in the University of Edinburgh, and we acknowledge Professor Ignacio Maria Viola and my colleague Suji for carrying out these experiments. And at last, keep an eye on my research group's work regarding this of the Bio FSI lab of University of Birmingham. And if you have further question regarding this, you can always contact me. And I leave the floor for asking me any question if they have. Thank you. Hello.
Sorry, thank you, Chandan. Thank you. We make applause to you, but we were mute, so you cannot listen. Okay, thanks for the nice presentation. Very good job, good quality. There are any questions from the audience? Yes, from Charles. Charles, maybe you can come here, so you can. There is a question from Charles Mocket that's coming here. Okay.
Yes. Hi, Charles.
Hello. Maybe you mentioned it, but I might have missed it. What's the Reynolds number based on the chord length for these?
So for this presentation, we are doing a Reynolds number of 20,000.
Thank you.
Thank you.
Chandan. Sorry, I think you have to run a lot of simulation. What is the time for one simulation, and how many in total you have to do for this DOE? Essentially, it's a DOE at the end of this story, right?
Yes. So I actually I should have given these estimates for this particular audience actually. So these simulations are done with different mesh qualities, but in an average, I would say they have around 15 to 20 million cells. And these simulations are run in the National Supercomputing System of UK, Archer 2. And these are quite expensive, and to get around 5 to 10 periodic cycle of these pleaching or plunging cycle, we take around 3 to 4 weeks actually.
Ooh. 3 to 4 weeks?
Yeah,
one simulation?
No, for 10 cycles. Yeah, depends on how many cycles we use and how many processors we are available to use. So normally one node of Archer 2 has 128 processors. So we normally try to run it with many nodes, but depends on the availability. So we have to go with the minimum loads, and then minimum nodes around like 16 nodes, I think, but maybe the details will be known by the PhD student. But I think 8 to 16 nodes we can run the cases, but I think sometime it is not available. And there is also a time limit of 48 hours in Archer 2. So we have to stop it. It will be stopped automatically. We have to restart it. And then we have to maybe wait for a queue for some time. So yeah, it takes a lot of time.
Good. You are burning a lot of CPU hours. Good. Well done. Good.
Yeah, I think this problem is very complex. So we need to know many cycles to understand what's happening actually.
Yeah, it could be interesting to try to optimize on HPC this calculation, even if you save some percent, could be nice.
Yes, I think, yeah, that's where the next direction should be. So I think we have to really focus on now optimizing the simulation, which we have not spent much time on.
Yeah, probably could be a chance to use the MGX from NVIDIA for the linear algebra. Maybe you can see the talk tomorrow. There we talk about that. Maybe.
Okay, I will attend surely. Thank you.
Okay, thank you, Chandan.
So last thing, I think I want to show this. Can you see my slide?
Yes.
Yeah, so I want to invite all of you to attend the training session that I am going to offer on dynamic meshing like the previous year on the last day, Friday, in the last training session. So if you are interested, please do come. Thank you.
Okay, Friday from 2:50 to 4 p.m. Thanks. Okay, online. Thank you again, Chandan, for your presentation. Thanks again.
Thank you.
Hello?
Yes, you can start, yes.
Yeah, now is better?
Yes, please start, please.
Okay, yeah. Thank you very much for introducing me. My name is Asmelash Haftu, and I am a PhD research scholar in Aerospace Engineering Department, Indian Institute of Technology, Bombay. So the presentation for today is vertical axis turbine simulation. using sliding mesh and overset mesh techniques of OpenFOAM. And the collaborators, these are the collaborators, Shiva Gopalakrishnan, Purnama Chandan, and Joel Guerrero. I guess Joel Guerrero will be there by now. So yeah, I'll continue. As an outline, I'd like to give some short introduction and then talk on computational methods, the sliding mesh and overset mesh, of course, and we'll see some results and discuss. So when one imagines about wind turbine, mostly one will be thinking of the horizontal axis turbine, but on the other hand, the horizontal axis is a turbine with axis is parallel to the flow direction. But this is the other version of turbine is a vertical axis, where the axis is perpendicular to the ground and the blades rotate around that. So for this particular topic, we are choosing Derace type vertical axis turbine with H rotor, because it is simpler for design and manufacturing and robust. And we can talk so many things about that, but I'd like to show this one. So a vertical axis turbine, if you consider this is a cross section on 2D, the blade rotating on a circular domain. So we can understand of this circular domain in two halves, upwind pass and downwind pass. So in the upwind, there is a clean flow, and when the turbine passes through here, it will capture more around 80% of the torque required by the position. And in the second half, since the flow will be disturbed, and then it will capture only around 80% of that. So the first figure is top view of a vertical axis turbine trajectory on using typical operating conditions like 6,000-7,000 Reynolds number based on core and free stream velocity 0.183, and for tip speed ratio or lambda 2.5. So the torque curve for this is shown in the second one. So in the red zone, so this first we have upwind and downwind, and then for detailed aerodynamic discussion we can see in 4 different segments. Like in this region, we have the highest torque. It depends on the tip speed ratio, it may go up or down. So because of this, when the turbine passes through the flow, it creates pressure differences in the locality, and this pressure difference will interact with the incoming upstream and with the wake downstream. So this creates more complexity pressure wave interactions, and it is a little bit complicated. So even if the wind speed is constant or the rotor speed is constant, always this complexity is there. So our motivation is we want to explore this aerodynamic aspect and using computational fluid dynamics. So the main objectives are the numerical simulation of the turbine using the 2 methods. So the next part is about some aerodynamics, some technical terms will be there. I think to speed up, I'll skip on this. The main parameter we need is the torque coefficient. We are calculating torque of the turbine. So in the first plot, we have the velocity vectors, and to calculate the relative velocity and angle of attack. And after that, the force vectors. So we have the tangential force coefficient, the tangential force and normal forces. So this is the relative velocity direction. So the force will be perpendicular to this lift force and parallel is drag, or it will be in the normal and tangential. So the resultant force is resultant of any of this group, and any small component will keep it driving forward. So in the computational method, I would like to talk about the solvers. We are using pimple-based algorithm, and for the sliding mesh, pimple form, and over pimple form for the overset mesh. So these are the simplified incompressible universal equations. We are incorporating this UG, which is a mesh velocity, to account for the moving wall boundary condition. So turbine specification. So we are using single blade turbine with airfoil cross section NACA 0015 or NACA 0015, chord length of 0.15 and turbine radius 0.61 for a Reynolds number of 6,000-7,000 based on chord. And this one we have 3 tip speed ratios 2.5, 5 and 7.5, and rotor speed is constant 0.75. So for the first one, the velocity will become like this. and for the others we will calculate. And using this turbine configuration, we choose a computational domain, which is a square domain basically, parameterized based on the radius of the turbine. This is R, which is 0.6, where the turbine rotates. For sliding mesh, we need a rotating body, so it will be 3 times R, and the domain size is 20R by 20R. So we have the inlet here, we define velocity, and in the outlet, constant pressure and gradient velocity. So the blood will be having moving wall boundary condition, and the overset patch will be the overset boundary. So using the sliding mesh, so I want to show only the mesh near the airfoil. Using a series of refinement levels, we have this kind of mesh around the airfoil, and to keep better property of the mesh around the airfoil, we use some layers. And then first choice is 1E-3, the minimum thickness near the airfoil. And with 10 layers of expansion ratio 1.15, we are able to use around 60,000 cells for the simulation. And with disabling these properties, we have maximum aspect ratio and skew ratio within the limit. And yeah, so many of the simulations of this type in turbine, they use around 1 million cells or 600 and more. So since we have limited computational resource, we are using this. Now, the first point, we wanted to study which airfoil we have to choose, because in the literature it says so many things like 21 or. So the basic thing here is airfoil, either you design your own airfoil or you choose whatever is there, like Mach series airfoils, especially the symmetric ones is okay because it interchanges phases in the domain. Now, for our case, depending on this particular Reynolds number, the thinner airfoil seems to be producing higher torque. But since, because of structural limitations of strength materials, then we don't want to go to 10 or 12. And then, how many revolutions required for the turbine to converge? We have simulated up to 24, so basically after 8, the differences is negligible. And we simulated using different turbulence models. And in the literature, widely used ones are SSG, K omega, and RNG epsilon turbulence models. So we go with 10 cycles and NACA 15 and RNG turbulence model. And based on this, the complete simulation of the turbine, which is converged, we have compared it with Euler et al. Using the sliding mesh. This is an experiment done in 1983. The experiment is not 100% accurate. It has some limitations, but it will give us a guide to where the results should be. So we have considerably very good matching for the tangential force coefficient and some differences with the normal force coefficient. So when we increase the tangential force coefficient, when we increase the tip speed ratio from 2.5 to 7.5 series of 6 simulations for increasing tip speed ratio, the torque reduces. This is because the angle of attack is reducing upon passing from low to high tip speed ratios, because tan inverse of angle of attack becomes 1 over the tip speed ratio. And then comparing a particular 5, the tip speed ratio equal to 5, matching is considered well. And this is what we done using the sliding mesh. And overset meshes, I think the basic details we have not included, but we have tried to create, meshes. The basic idea here is the meshes are created separately. We have airfoil mesh separately and background mesh separately, and we merge the meshes and creating the overset patch for the interpolation of files. So our initial simulations were having more oscillations and under prediction and yeah, something like that. So based on that, we have experimented on several combination of schemes, like gradient scheme with a divergence scheme, first order, second order, with turbulence which works, which does not work. So we tried on this, changing the overall size of the overset mesh and the shape of the overset mesh, like elliptical body And so we are able to see this one will be giving better smooth results with less oscillation and more accurate. Because at least we are able to maintain one-to-one matching of the cells of the overset and the background at the intersection. So also we have to choose the overset interpolation methods, cell volume, weight, inverse distance, least squares, and track inverse distance method. So least squares is mostly taking a lot of time, like for example, this simulation for 2 seconds of part of the turbine. Then with turbulence, it will increase further. And the least square becomes more oscillatory and it is time taking. And I think it is difficult with moving bodies. And the last one is difficulty having with tracing the holes. The first two are very good. Cell volume, weight, and inverse distance. So we are using inverse distance for the simulations. So also we have added local time stepping for and varying control, CFL control or the current number. And based on this, we are able to get a little faster and with less oscillation convergent results. So the numerical parameters here, yeah, these are just what I discussed earlier already. Euler first order is used with the overset and backward for the sliding mesh techniques. So in the solver, FV solution, this is the best working parameters for the overset, whereas pressure can be solved using multigrade method in the sliding mesh. So the comparison of the results with the sliding mesh. So the sliding mesh, the overset mesh seems to have more kinks, but the overall has captured the result accurately. And comparing 3 of them with the experiment, it seems over 1 cycle, there is over 3 cycles, so over 1 cycle. So it only shows a little bit of our results are shifting to the left. And yeah, small variation in the peak also is observed. That is, otherwise the prediction can be considered very good. So the overset mesh only shows more kinks here and there. And sliding mesh will have captured more torque on the downstream. So some video clips of this one is using the sliding mesh, but here we want to show only the motion of the bodies. So in the sliding mesh, first part is sliding and this one is overset. So we are able to move the airfoil only, but here we are rotating the big body. So it needs to maintain some kind of axial symmetry. So even though this method is very good for kind of vertical axis turbine or horizontal axis turbine simulation, and it is better accuracy, but if you want more modifications, it will be challenging. So some vorticity distributions here. This is based on the sliding mesh, and this one is the overset mesh for the same scale of simulation. And we can observe some kind of similarities after 180 revolution and after 2 cycles of the distribution. So the strengths and limitations we have observed here, the sliding mesh is a suitable model, like for the basic turbine cases, and it is accurate and computationally efficient. But in the intersection, it can lead for mesh distortion near the interfaces. And if the geometry is complex or you have complex motions, this may not be useful. It can also result in poor quality meshes when there is mesh distortion. On the other hand, the overset mesh can handle complex motions and geometries. Like any complex motion, or if the geometry is complex, or if you have multi-bodies, like for example, multiple flapping wings and oscillating cylinders with large relative displacement. So this will be the main option. So it maintains the mesh quality close to the moving objects because the mesh is created separately for the airfoil. You can maintain the best quality mesh for that particular model. So modeling of multiple moving bodies like overtaking of cars and so on can be possible with this. So the problems we have seen here is the interpolation methods are not mass conservative and the results are sometimes diffuse. So you will have to experiment a lot to get a better working condition. And also sometimes it looks computationally expensive. For example, I have simulated 2 airfoils. If you add third airfoil, it's some kind of limited mesh, and we are not able to expect by how much it will delay the simulation. So these things are not resolved properly. Yeah, so I keep it short for the time we waste. So we have done the validation in comparison of the two methods. The OVERSET mesh can be used for exploring innovative designs. For example, if you want to pitch the blood while it is moving at the lower angle of attack or in the high drag areas, so this can be incorporated. Or some other designs like 2-axis turbines, so this can be best. So the future work will be a complete design of and performance analysis of a turbine. And thank you for your attention and acknowledgements. First, I'm an Ethiopian student, external student in IIT Bombay. So due to some devastating civil war in my country, all my financial resources and other things were a difficult condition. And for about 3 years, and those organizations have helped me a lot to reach at this point. The Institute of Technology, Wolf Dynamics, they gave me free OpenFOAM training in 2020 by Joel Guerrero. And this is the third offer for the OpenFOAM Workshop, online present and grant. So I can't be thankful enough for these people. So thank you very much. Yeah.
Thank you for your
Hello?
presentation.
Hello? Can you hear me?
Yeah. We can hear you. Yeah. Thanks for your presentation.
Yeah, we are
Sorry.
struggling. At the end, we are struggling to connect. Yeah.
Sorry, it's very noisy on our side because it's ringing all the bells of the church in the center right now. So it's very noisy. Sorry.
Okay, no problem. But my voice was audible little bit.
Yeah. No, we hear you very well. The problem is from our side. Now there is a lot of bells ringing. Okay.
Okay. Thank you very much. Yeah.
Sorry, there are any questions from the audience? Not. If not, I have just curiosity. You told that there is a difference in computational efficiency between OVERSET and sliding. What is, in your case, what is the difference for make one simulation with OVERSET and one with sliding mesh in terms of time?
With sliding mesh and OVERSET mesh.
Yeah.
In terms of time?
Yes.
So the OVERSET mesh difficulty we have seen is, for example, if I simulate with one turbine, one blade, it will take some time. And then if I add second blade with some, like, for example, 10,000 cells, it will delay the simulation. So this factor is not clear by how much it will delay. Otherwise, the time they are almost, for similar, we are taking around 60,000 cells for both cases with minimum cell length 0.001 for a particular Reynolds number. And the time is around 6 hours it will take on 16 cores for 10 revolutions. But using for the OVERSET one, using the CFL control and local time stepping, we were able to get faster convergence around third revolution. So in this case, it will be faster. But their time is also not that much different. The only problem is the OVERSET has inaccuracies. Like, for example, it is not mass conservative, so you have to create a very good quality mesh to improve the accuracy. And with that respect, the sliding mesh is considered more accurate, but this one has more flexibility. If you want some innovative designs, for example, the turbine, as you have seen, I shown one curve at the beginning. So 80% of the torque is captured at the beginning, and then negative, and then some. So this is cyclic loading on the turbine. So it creates fatigue load for the turbine to shorten its life in the long run. So yeah. So for this reason, some innovative methods are required to improve the torque capturing in the lower cases. This is done by pitching the blood. So it can be done using the overset mesh, not the sliding mesh. Because the sliding mesh must maintain symmetric kind of bodies with arbitrary mesh interface to interpolate the data from the stationary to the moving bodies.
Okay, thanks for the clarification.
Thank you very much.
Okay, if there is no more question, thanks again.
Okay.
And we can close the session.